something in the sky. What does that mean? Now we have hours of videotape from the United States Navy. We can measure the data from these videotapes. We now know that these objects can travel between Mach 5 and Mach 20, up to 20 times the speed of sound. They can drop 80,000 feet within a matter of a few seconds. Not only that, they can also fly underwater.
If a planet is too close to the sun, then the oceans boil away. Yeah. If a planet is too far from the sun, the oceans freeze. You have to be just right from the sun to have liquid water, which is the universal solvent. It's where DNA first gets off the ground.
So what's the next step here for scientists?
The next step is we want to look at the atmospheres of these planets. We want to look for oxygen, water vapor. We want to look maybe even for radio transmissions. Perhaps there's intelligent life there. Perhaps they've harnessed some kind of radio.
This image is truly tantalizing. But why is it so captivating? Since its discovery over 100 years ago, it has mesmerized astronomers worldwide. It lies frustratingly close, yet it would take generations to reach. Although it's not visible to the naked eye, it is the closest star to our solar system. At one point, it was the lowest luminosity star known to humanity, yet paradoxically, it is also the most active. As if the contradictions surrounding this star weren't alluring enough, scientists have recently discovered a seemingly Earth-like exoplanet in its orbit. This revelation has sparked discussions about interstellar colonization, involving figures like Mark Zuckerberg, Elon Musk, and Stephen Hawking. It's almost as if this star is playfully toying with our insatiable curiosity about what lies beyond. If you're anything like me, you can't wait to absorb everything there is to know about this enigmatic star. Join us today as we embark on a whirlwind tour of the Alpha Centauri star system, from the binary stars Alpha Centauri A and B to a deep dive into everything we know about Proxima Centauri, its recently discovered planets, a controversial potential discovery, and the flyby missions that the future might hold. Leaving Earth, it would take just over 4 light-years to reach the closest known stars to our solar system. I say stars because they are technically a triple star system collectively known as Alpha Centauri. This system comprises Rigil Kentaurus, Alpha Centauri A, Ptolemy, Alpha Centauri B, and Proxima Centauri. Together, Rigil Kentaurus and Ptolemy form the binary star system Alpha Centauri AB, located 4.37 light-years away from Earth. Both are sun-like stars orbiting a common center every 79.76 years. If you're south of the 40th parallel, you can see them at night, although to the naked eye they appear as a single star, the third brightest in the sky, behind only Sirius and Canopus. The binary Alpha Centauri system was discovered in 1689, but it took over 200 years for the third star to reveal itself. In 1915, luck smiled upon a Scottish astronomer named Robert Innes, who was the director of the Union Observatory in Johannesburg, South Africa. While comparing photographic plates with the help of a blink comparator, he observed that a faint star had moved in the 5 years between photos. This movement was similar to that of the Alpha Centauri binary star he was observing. After further investigation, he concluded that this new star was closer to the Sun than its twin siblings, a finding quickly confirmed by his contemporaries. Paradoxically, it became both the closest and dimmest known star at the time. The surprises didn't end there. In 1951, American astronomer Harlow Shapley discovered that Proxima Centauri is a flare star. Not only that, but it was the most active flare star known back then. Over the last 70 years, Proxima Centauri has become a hotly studied star, no pun intended, and with the recent discoveries of an Earth-like exoplanet orbiting it, I believe that interest will only intensify. But I'm getting ahead of myself. Let's get to know this star a little better before placing such grand expectations on it. At 4.24 light-years away, Proxima Centauri is slightly closer to us than Alpha Centauri AB. It is a main-sequence red dwarf star with an estimated mass of 12.2% and a diameter of 15% that of our Sun. Despite its smaller size, Proxima Centauri is about 40 times more dense than our Sun. Due to its low mass, the interior of the star is entirely convective, creating a magnetic field around it and leading to the sporadic release of magnetic energy in the form of flares. As a result, Proxima Centauri randomly experiences drastic changes in brightness and energy emissions. On May 6, 2019, a flare event on Proxima Centauri was observed as the brightest one ever recorded. These flares release radiation across the electromagnetic spectrum, including X-rays. To give you an idea of Proxima Centauri's solar activity, its baseline X-ray luminosity is roughly equivalent to that of our Sun, a much larger and hotter star. This level can increase by up to 2 orders of magnitude during a flare. Not only does Proxima Centauri have more intense solar activity than our Sun, but it also has a higher frequency of it. It is estimated that 88% of the star's surface is active at any given time, which is significantly higher than our Sun, even at the peak of its solar cycle. However, before you start envisioning Proxima Centauri as a fiery ball of fury, remember that we are comparing apples and oranges here. Our Sun is not a red dwarf. In fact, compared to other red dwarfs, Proxima Centauri is considered to have a low activity level. Unlike our Sun, which scientists estimate will only burn through 10% of its hydrogen supply before burning out, Proxima Centauri is predicted to use up almost all its fuel before leaving the main sequence in about 4 trillion years. By then, Earth, our Sun, and our entire solar system will be long gone. Alpha Centauri AB is 0.13 light-years, or about 2 trillion kilometers, away from Proxima Centauri. You may be wondering why Proxima Centauri is considered part of the same stellar system if it is so far away from its companion stars. Well, we have data that shows it is gravitationally bound to the Alpha Centauri AB binary star, making it part of the stellar system with an orbital period of about 550,000 years. How it ended up in this orbital situation is still open to speculation, but 2 main scenarios seem plausible. Either Proxima Centauri was bound to the Alpha Centauri system during its formation, meaning the stars likely share the same elemental composition, or Proxima Centauri was captured by the binary star's gravity during an encounter, leading to a highly eccentric orbit that was later stabilized by the galactic tide and further stellar encounters. Regardless of how Proxima Centauri got into this triplet, calculations suggest that in 3.5 billion years, it will unbind from the system as Alpha Centauri AB continues to evolve and lose mass over its lifetime. The binary star system itself is also predicted to disassociate and diverge in about 12 billion years into 2 white dwarfs, which will forge independent and steadily diverging paths. Being our closest neighbors, we know quite a lot about Alpha Centauri AB, but we'll delve deeper into this binary star system in another video. For now, all eyes are on Proxima Centauri. The search for exoplanets around Proxima Centauri has been ongoing since the mid-2000s without much luck, but researchers weren't willing to give up. Not only was this star our closest neighbor, but it is also a red dwarf, with 20 to 40% of such stars having a planet orbiting in a habitable zone. The patience paid off. Observations at the European Southern Observatory in Chile identified anomalies in Proxima Centauri that couldn't be explained by flares or other solar activity. The data seemed to indicate there may be a planet orbiting it. In January 2016, the Pale Red Dot campaign, a coordinated effort from multidisciplinary scientists and ground-based telescopes around the world, was launched to see if this suspected planet could be identified. In August of the same year, the discovery of exoplanet Proxima Centauri b was announced. It is at least 1.07 times larger than Earth and sits 20 times closer to Proxima Centauri than we do to our Sun. This exoplanet orbits its star in just 11.2 Earth days. Even though Proxima b is within Proxima Centauri's habitable zone, that doesn't mean it could sustain life. There are many other factors that determine habitability beyond just the presence of liquid water. For one, the intense solar activity would bombard the planet with 10 to 60 times the amount of UV and X-ray radiation we receive here on Earth. We'd need to develop SPF 3000 to make the journey worth it. Another factor to consider is whether an atmosphere could survive under such conditions. As far as we know, atmospheres are vital for maintaining a water-friendly surface pressure, providing protection from dangerous space weather, and regulating planetary climate. The radiation Proxima b is exposed to might be enough to strip away the key components of an atmosphere over time. Frustratingly, we don't know much about Proxima b beyond its distance from its star and its orbital period. It is unlikely to have any moons due to the instability of their orbits over larger timescales, but it is thought the planet itself is tidally locked to its star. As discussed in a recent video, this doesn't bode well for potential habitability. It likely developed under extremely different conditions from Earth. Assuming it formed at its current distance from its star, it would have gone through a much faster evolution with stronger impacts and less water. However, there is some debate about its formation. Some scientists think the amount of material in the protoplanet disks would be insufficient for it to form at its current distance from the star. They argue that it is more likely the planet formed farther away from its star and eventually drifted into its current orbit around Proxima Centauri. What the surface of the planet might look like is purely speculative. Theories range from a planet covered in ice to one with planet-wide oceans like Earth. Though unlikely, if the planet is indeed tidally locked, it could be a water-free world with only dry land or a subsurface ocean like Europa. In short, we have no definitive idea about Proxima b yet, as we haven't directly imaged the planet. We'll have to wait for the first flybys to get a better understanding, which some moguls are already planning. If it happens, I have a feeling it will be just as groundbreaking as the Voyager flybys in the 70s and 80s. But more on that later. 6 years after the discovery of Proxima b, news of Proxima d swept global headlines. The first signs of the planet emerged in 2020 when a weak 5.15-day signal was detected in the radial velocity data during a study of Proxima b's mass. Following further data collection and analysis, scientists announced the discovery of Proxima d in February 2022. So far, we know it's a sub-Earth planet with at least 25% the mass of Earth, orbiting the star every 5.1 days at a distance of 4.3 million kilometers. It orbits too closely to have a habitable equilibrium temperature, which would be driven up to 87 degrees Celsius. It's also likely tidally locked and would be bombarded with so much radiation that the chances of finding life there are very slim. However, this planet holds promise in another realm. It is the lightest planet ever detected using the radial velocity method. Since the planet is too far to be seen with telescopes, scientists rely on a characteristic wobble anomaly in the movement of a star that indicates the potential presence of a planet. The more massive the planet, the more obvious the wobble. In the case of Proxima d, the wobble was practically imperceptible. The fact that we caught the wobble and were then able to demonstrate with enough certainty that it is caused by a planet is a technological milestone worth celebrating. If only the world of astronomy were so cut and dry. Where there is breakthrough and celebration on one hand, there is bleak uncertainty on the other. That's exactly where you'll find the controversial exoplanet Proxima c, initially detected in 2019 using the same radial velocity method that found Proxima d. The existence of Proxima c was confirmed in 2020 using Hubble astrometry data. However, in 2022, another team challenged the initial radial velocity data that led to the alleged discovery, claiming the anomalies could have instead been associated with small, unaccounted systematic errors in the data extraction method. The trouble arises from the fact that, unlike Proxima d, which orbits incredibly close to the star, the data for the alleged exoplanet Proxima c places it very far away from its star, with an estimated 1,928-day orbit. There is no similar example of a wobble detection of a planet with such a low amplitude at such a long period. That doesn't necessarily mean it's wrong, but it's going to require some confirmation from additional observations, says Paul Robinson, an astronomer at the University of California, Irvine. If Proxima c does exist, it will take a bit more data to convince reluctant skeptics. If it does not exist, it remains unclear why the Hubble astrometric data was able to corroborate and confirm a planetary signature. I guess we'll just have to wait and see what future studies find. With the recent discovery of Proxima b and how relatively close Proxima Centauri is to us, it is a perfect candidate for a future flyby. However, reaching our neighboring star system will take thousands of years using conventional propulsion technologies. Newer techniques like solar sails or nuclear propulsion might make such a trip possible within a human lifetime. Such ideas spearheaded the development of Project Breakthrough Starshot, an initiative set up by investor and physicist Yuri Milner, which aims to reach the Alpha Centauri system within the first half of the 21st century. The idea is to conduct a flyby mission by sending microprobes weighing just a few grams at 15 to 20% the speed of light, and they think they could do it as early as 2036. With this timeline, the probes would reach Alpha Centauri in 20 years, and we on Earth would receive the first data 4 years later. After the initial flyby, the probes would possibly venture to the exoplanets and collect data on their atmospheric compositions, much like the Voyager missions did in our outer solar system decades ago. The team is pinning their hopes on the yet-to-be-developed star chip, a microelectronic, gram-scale wafer-carrying cameras, photon thrusters, power supply, navigation, and communication equipment, essentially constituting a fully functional space probe. This is based on Moore's law, which states that the speed and capability of computers can be expected to double every 2 years. Bold and ambitious, the plan is not without its challenges. The team proposes to power these microprobes with 100 gigawatts of Earth-based lasers. That's the equivalent of the output of 100 large nuclear power plants, concentrated on probes just centimeters wide. Plus, all components of these tiny probes must be built to withstand extreme acceleration, cold vacuum, and collisions with space dust. With this in mind, perhaps the project would more aptly be named Project Breakthrough Longshot. But if the history of space exploration has taught us anything, it is that missions confronted with cruel hardship and slim odds can emerge as triumphant milestones of humanity. Proxima Centauri might just be the next one for the history books. Let's just hope we are around to see it. As telescopes like the James Webb look out across the Milky Way, you might have heard the growing buzz around newly discovered exoplanets. It wasn't that long ago, only 1992, that we found the first planet outside our solar system. Since then, over 5,500 have been confirmed in the relatively small area of space, only a few thousand light-years across that we reside in, while the Milky Way itself is roughly 100,000 light-years in diameter. This offers us a tantalizing promise of billions to trillions more across the rest of our galaxy. Every star, on average, likely has at least one planet, and perhaps several. With all of these exoplanets out there just waiting to be found, it's only natural we would want to turn our thoughts towards Goldilocks zones and planet habitability. After all, humanity has its eye on colonizing the stars, and an Earth 2.0 is surely waiting for us out there. Mathematically speaking, in fact, you might have already heard that phrase, Earth 2.0, being delivered in headlines of articles or videos claiming that a planet has been discovered that would be ideal for human life and colonization. However, don't believe the hype. All the planets we have found so far, to put it scientifically, suck. And once you hear what I'm about to tell you, you'll agree that moving to any of them will be the last thing any sane person would want to do. When choosing an Earth 2.0, just like with building a house, it's a good idea to start by establishing your non-negotiables. Some of this is fairly simple to consider. For instance, temperature. You want a nice temperate climate somewhere it's not too warm and not too cold. Given that temperature drops the further you are from the sun, every planetary system has a sweet spot where the temperature of a planet is likely just right. Not too hot and not too cold, similar to Goldilocks and her bowls of stolen porridge. As a rough rule of thumb, if a planet is at the right distance from a star, it may well have a suitable temperature for us to set up shop. Of course, This is in no way a guarantee. After all, Venus, a planet residing in this zone, in theory, should be perfect, but its choking atmosphere makes it the hottest planet in our solar system, despite its relative distance from the Sun compared with Mercury. So, atmosphere also plays a part in all this. Speaking of atmosphere, that's also something you'll want to look for in Earth 2.0. Ideally, something with oxygen and water vapor, and without anything that would poison us, but at least something that could trap heat in and offer some protection from space radiation. However, sometimes a non-negotiable is simply the neighbors that live close by. So let's consider the first major reason why most of the galaxy's exoplanets fall short: their neighboring stars. Our own star is known as a G-type yellow dwarf, a relatively fast-burning, short-lived sort of star, at least compared to some of the other options out there. Stars like our Sun tend to live for 10 billion years before they collapse and transform into a red giant. It is stable, and that stability has been useful for the life that eventually flourished here. However, yellow dwarfs are far from common in the Milky Way. They represent only 10% of the total stars. Far more common in occurrence are the long-lived red dwarfs, which make up 75% of the stars in our galaxy and can live for around 14 trillion years, longer than the universe has existed. This means we've never seen one die, so to speak. Unfortunately for the planets orbiting them, red dwarfs come with numerous drawbacks. For starters, red dwarfs have a much closer Goldilocks zone compared to their yellow cousins. They burn less brightly, with luminosities between 10% and a mere 0.00125% that of our Sun. Unless you want to live on a world shrouded in perpetual night, which sounds cold and depressing to me, and will make growing plants a bit of a challenge, you'd want an Earth 2.0 to be a lot nearer to its red dwarf to compensate. This wouldn't be a problem in and of itself if it weren't for the second characteristic of red dwarfs that makes them very unpleasant neighbors: their instability. Our Sun is the main source of our space weather. It shoots out a frequent stream of solar winds, flares, and coronal mass ejections. However, this doesn't compare to the amount of space weather created by red dwarfs. Flares from red dwarfs can be 100 to 1,000 times more powerful than those emitted by our Sun. The frequent bursts of plasma and radiation coming from red dwarfs are powerful and dangerous enough to strip away the atmosphere and even boil liquid water on planets in the habitable zone. Given how much closer planets are to their star in a red dwarf system, the odds of life getting enough time to arise before being hit with a life-sanitizing dose of X-rays are pretty slim. If you want to live on a planet around a red dwarf, you'll likely need some serious sun cream. This rules out many known exoplanets, such as astronomer favorite Kepler 186f, which some scientists hoped might be habitable. While it may be possible to live for a time in quite uncomfortable conditions in a deep underground bunker on such a planet, the experience would hardly be pleasant. But even during periods between harsh solar weather events, there's another problem with planets around red dwarfs: their tendency to be tidally locked. Being tidally locked means that the same side of the planet always faces the star as it orbits. There is no rotation between day and night. One side of the planet is in perpetual heat, and the other side is in permanent shadow. Due to gravitational constraints, planets near their Sun have a tendency towards being tidally locked. Just take a look at Mercury, with its day that lasts 176 Earth days or 2 Mercurian years. This lack of rotation could render most of the planet uninhabitable. You'd either face scorching deserts on the day side or freezing ice on the night side. Even if humans tried to live in the narrow band of twilight that would ring a tidally locked planet, liquid water might prove difficult to find. Any moisture in the air that found its way to the night side of the planet would get locked there, solidified as ice. Overall, the planet would be very dry, and even in the twilight zone, there would be no rain. And that's not to mention the low power of a magnetic field that would likely be found on a tidally locked planet. The dynamo effect that powers the magnetic field on Earth is thought to be influenced by the Coriolis effect, the rotation of the Earth imparting momentum to rising and falling liquid metal in its core. Without this rotation, Such a magnetic field would be inevitably weaker. So I'm sorry to say that this rules out planets such as Proxima Centauri b. Our closest exoplanet, Proxima Centauri b, is otherwise an interesting candidate. Its closeness makes it one of the easiest planets to get to for us, situated only 4.2 light-years away. It's thought to be a rocky Earth-like planet, which is convenient, as living on a gas giant would be challenging to anyone with a fondness for solid floors beneath their feet. Most compellingly, its mass and radius are very similar to Earth's, meaning it has a similar gravity. Why is this important? Let's compare it with another Earth 2.0 contender, Kepler 452b, the first planet to ever be referred to by that title, and the planet described by a NASA scientist as the closest twin to Earth. Kepler 452b has much to recommend it. It is orbiting around a yellow dwarf like us at a similar distance. This means it's in the Goldilocks zone that makes liquid water on the surface possible. However, it is a super-Earth, meaning it has a mass and radius combination that makes it about twice that of Earth when it comes to gravity. Well, that's enough for today. If you really enjoy the video, then don't forget to subscribe, like and share the video. Also stay tuned with us for new discoveries. Thank you.